Welcome students, we will continue our lecture on runoff, that is unit 5. Okay, last time we discussed about the various catchment characteristics, right? And then we winded up the last time's class by giving you a simple assignment which you were supposed to do. Okay, if you have not yet done it, I would highly recommend you do it. If you are doing it, good. If you encounter any problems, I'm always there to help. And let's continue our today's lecture. So in today's lecture, we are going to discuss about the runoff volume, or also sometimes known as yield. Okay, so as there is rainfall, as the rain falls over a catchment, then you know that after it satisfies the initial abstractions, then the remaining water flows into the stream and eventually drains into the ocean, right? So here, how much water is being carried by a particular stream or a river is what you call by runoff or yield of that river. Okay, and like precipitation, this runoff is also a random, because runoff is generated by the random input. Yes, precipitation is random, and because of precipitation there is runoff. So there is some randomness in precipitation as well. There is seasonality, okay, but still then it is runoff, it is random. So instead of using the parameters like average runoff, people usually use the term dependable yield. Okay, so this dependable yield, for instance, if I say q is equal to, let's say, 10 meter cube per second, is 75% dependable for Guangzhou. Now what we are saying here is it gives us an information that for the 75% of time, the water in Guangzhou is going to be 10 meter cube per second. So that is called dependable yield. Okay, so now it connects the time as well as the value. If you give an average value like, let's say, 12 or 15, that does not give any time. It is the average of all the seasons. But when you give the 75 percentage dependability, then it says that 75% of the time, that much value, the 10 here in our example, 10 meter cube per second is available in this river. So that's how we associate dependable yield with the runoff, so that it gives us an information about the runoff characteristics of the catchment. So there are basically three methods. Okay, now I can also include fourth one here, although it is not there in your syllabus, but there are four methods to do it. Okay, so the last one is modeling. Okay, last one is the hydrologic modeling. So first one is the rainfall runoff correlation. You can find the runoff using rainfall runoff correlation. For this you need a heavy data, you need a long-term data. Okay, next one is the SCSCN method. There's a new it's a different method, okay, to compute the runoff. It is empirical in nature, but because now it has gained so much of popularity, it deserves its own place. And there are other empirical equations, like I have been explaining this. Certain studies are being carried out at a specific location, and you derive some relationship for that location, only applicable at the location where the study was conducted. So these are what we call by empiricals, and there exists some empirical charts, tables, and equations, but nowadays we don't use this. We don't use this, and it is not advisable for you guys to use it, even because it is not thoroughly tested for other catchments. So instead of using empirical, now we substitute with modeling. Many softwares are available now, free and open source. Some are free, it's not open source, but some are free. So now you can do modeling because the data is available, everything is available. Computer, we have a very powerful computers these days, and modeling is feasible. So we use modeling to compute the runoff. Okay, so there are In the syllabus, of course, we have to study the rainfall runoff correlation, SCSCN method, and there are empiricals. But in real field, we basically use modeling. And in modeling, yes, of course, the SCSCN method is incorporated in modeling. So we can just merge this modeling in SCSCN method together. And there are other methods like kinematic wave, and there are other so many things. But yeah, the modeling is with the help of a model, then you can predict the rainfall runoff from a catchment. Okay, moving on with the first one, that is rainfall runoff correlation. Like I said, rainfall runoff correlation means you're applying the linear regression analysis to establish a relationship between rainfall and runoff. In a sense, if there is this much of precipitation, how much would be the runoff? This answer is provided with the help of an equation which relates runoff of a catchment with precipitation, and there are some arbitrary constants. If you closely look into this equation, it's an equation of a straight line where a is the slope of the line and b is the intercept. Okay, so how to compute this a and b, I have shown in number of lectures. There are many methods. There are graphical method, and I have also used a concept of graphical method to derive this value a and b. And also I have explained you the analytical approach. In analytical approach, we use this formula to calculate the value of a and b. Okay, this is if first thing, how do you know that whether the relationship is linear or not? First thing, you have to plot your data. When you plot your data, if it is coming like this, then of course you can fit a linear line. But if your data is something like this, if your data points are like this, then it is obvious it is not a straight line, right? You cannot fit a linear regression here. You cannot apply this linear regression here. First you plot it, then you see the shape of this curve or a line. If it is linear, then of course go by this method. If it is non-linear but exponential, then the runoff can be expressed as beta pm, where beta and m are the coefficients. Use the logarithmic transformation to make this equation into a linear equation in a log graph. Okay, so if you plot the same value in log graph, you're going to get linear. That is what it means. And from here, you again, now if you closely see this equation and this equation, it's one and the same thing. Okay, so there is a parameter, there are two parameters. So here L and beta is the intercept and m is the slope. So we use this technique to find the parameters. Okay, that is for rainfall runoff. Now let's look a little bit deeper into this concept. If your data is very close to the, let me use a different color, what's color, blue, okay, thicker one. So if your data points is very close to this trend line, then we say positively correlated. And positive because when x value increases, y values increases. That is what we call it positive. If this data points are not very closely closely located with the trend line, then we call it weak correlation. And we see the trend line. If the values of increase with the increase in x, if the y is also increasing, with the increase in precipitation, the runoff is also increasing, then we call it weak correlation. This case may not happen in rainfall runoff studies because this is absurd. Because runoff depends upon the rainfall. It cannot happen that when rainfall increases, runoff decreases. That cannot happen. But if the data exists in this fashion, we say it negative correlation. Okay, but for rainfall runoff studies, this will never happen. These conditions will never happen. This could happen depending upon the catchments. Okay, this could happen. It could be sparsely located where you cannot fit linear or a logarithmic trend line, but this kind of data can exist. But negative correlation is until and unless you are using a rainfall of one catchment and the runoff of a different catchment, which is absolutely illegal, it's non-logic, there's no logic in it. So that time you may get this, but in the real world, for rainfall runoff correlation, you will never get this situation. Okay, Now here we are on SCSCN method. It was first formulated by Soil Conservation Services United States in 1969. Thereafter it has been widely used. Okay, it is widely used. In fact, most of the models, like I explained modeling, right, most of the model, it is inbuilt. The SCSCN method is inbuilt in the model, so you can simply click on the method to choose a method and then you can do the modeling. Okay, it it depends upon assumption. It is a conceptual method, okay, and it assumes that ratio of actual retention, okay, the catchment has some retention power, right? I mean, when there is a rainfall, all the rainfall is not going to go as a runoff. Something will be retained by the catchment. Yes, that the ratio of actual retention to potential retention is equal to the ratio of actual runoff to the potential runoff. Now potential runoff would be, the volume of potential runoff would be equal to the rainfall, because potential runoff means if there is no losses, then how much would be the runoff. So that the volume would be how much rainfall has occurred, that much will have to go to mass balance, right? We can also use the concept of conservation of mass. So that much volume of water has come, that much volume of water has to leave, or else there is some mass is getting destroyed in between, so which is not possible. So from here we have the first equation, that is the effective precipitation, which is the potential precipitation minus some losses, right? That is effective precipitation, effective rainfall we call it, is equal to, that is equation number 1. Let's keep it as equation number 1. And Q, which I'm saying as runoff, is equal to the effective runoff, right? Effective this precipitation, because I'm just subtracting the initial losses, okay? And then you have to subtract the infiltration losses, right? Together with infiltration and the initial losses and the infiltration, we call it total losses, but here I'm doing it separately. So for rainfall, I'm just simply subtracting the initial losses, because directly from the rainfall there is an initial loss, and for runoff, then I'm subtracting the infiltration loss. So from the assumption Q by P, the potential, what is this, the actual retention to the actual potential retention, right, is equal to the actual runoff to the potential runoff. So from this assumption we can derive this equation number 3. From this we again assume that initial abstraction is a function, is a fraction of potential retention. So here we are saying the initial abstraction is a function of a total retention multiply with the coefficient. So we are simply multiplying with the coefficient. What it says is IA is directly proportional to S. Now IA is equal to a coefficient S. Okay, that's what's been done here. Now using all these equations, we finally express our Q as P minus lambda S square divided by P plus 1 minus lambda S, where S is the retention, right? Storage, in other sense it is storage. And it is found from experimentation that alpha of 0.2 can be assumed. So from this, in this equation you can simply substitute the value of alpha as 0.2. Precipitation will be known, right? Precipitation, rainfall will be known. The value of lambda is taken as 0.2. The only unknown value is the retention, that is the storage. Now a concept of curve number is used to calculate the value of that storage, and it is that's why it is called empirical method, because this curve number you don't have an exact this relationship has been derived from experimentation. Okay, so you cannot theoretically derive this equation. It is derived experimentally by conducting so many experiments in the field. So it is said that storage is equal to 254 times 100 divided by Cn minus 1, where Cn is the curve number. Okay, now this curve number value ranges from 0 to 100, where for impervious surface. Okay, impervious surface means there's 100 percentage of runoff. Okay, and for natural surface it is going to be, the curve number is going to be less than 100. Okay, for impervious, when there is no losses at all, then we call it 100, or else it would be less than 100. Okay, so once you know the curve number, and this curve number depends upon the soil type and the antecedent moisture content of the catchment. We'll discuss about this, what is soil type and the antecedent moisture content. So for now, what you need to understand is the storage S is equal to this function, whereby a new parameter comes, curve number. This curve number depends upon catchment, CATCH, catchment characteristics, CS characteristics. Okay, so these values are, the curve numbers are usually available. It is available as a standard, so it depends upon what kind of soil and what kind of land use is there in your catchment. Depending upon this, curve number is available. It is standard and it is available in a tabular form. Okay, and the curve number, as I said, depends upon the soil type and the antecedent moisture condition. If the soil is sandy, then there will be less runoff, and this sandy type of soil is classified as low runoff, and it is classified under hydrologic group A category. Okay, hydrologically there are 4 categories of soil: A, B, C, D. Okay, A means A means low runoff potentials. So sorry, the sand, which example that I was giving is for this one. High runoff potential is sand. This is for clay. If the soil is clay, then there is low runoff potential. What I am saying now. Okay, let me repeat this. Okay, if the catchment area is sandy, because sand has the high potential of infiltration, the runoff will be less. So this is sand. Okay, if it is a clay type of soil or clay loam type of a soil, then it does not have the potential to absorb the rainfall. So what happens is, all the rain will drain as a runoff, so it has high potential. So this is clay. Did you understand the logic here? So once again, if the soil is sandy, what happens is, it has the huge capacity to absorb water, which we call at infiltration. So once there is a precipitation over the sandy soil, it infiltrates, huge volume of water infiltrates, so that amount of water for runoff is less. So we call it as low runoff potential. So it is classified under group A, sandy soils. And the clay soil has a less capacity for infiltration. So what happens is, all the rainfall that is falling over a clay soil, it simply drains out as a runoff. So it is classified under hydrological group D. Again, it depends upon antecedent moisture condition. Antecedent moisture condition means how much moisture condition was already available. So if condition A is, it was completely dry, it is average. Condition 2 is, and third one is, sufficient rain has occurred within immediate 5, which means soil is completely saturated. Now let's take the condition here. Okay, same condition. Now if the sandy soil is completely saturated, it also will have the high potential for runoff. This one already had a high potential of runoff. Even if this is whatever the little bit of capacity it had to infiltrate a little bit of water, if that is also saturated, then even higher runoff will be generated. So amount of moisture content, in a very simple term, moisture content in a soil also depends the runoff. Okay, now let us also discuss about this hydrological soil classification. So if you look this triangle, I hope this was introduced to you in your soil mechanics class. Okay, if it is not, then kindly look at here. You take a soil sample and you, by percentage, you find out how much clay is there, how much silt is there, and how much sand is there. And how do you know whether it's a clay, sand, or silt? Is by the particle grain size. Let's say in a sample it had 30 percentage of sand, okay, 70 percentage of clay, and 40 percentage of silt. In a sample you collected from a site, it consists of 30 percentage of sand, 70 percentage of clay, and 40 percentage of silt. So now this soil, the soil that you have brought in, falls in which category? So for this you simply trace this line, okay, you oops it's like this. For sand you trace this line, okay, and I mean now the soil that you have brought in falls in this category. Maybe my example was not very correct, so let me give a different example here because it is not coming up to any point. So let us assume about 35 percentage of clay, okay, 30 percentage of the sand, and let's say 40 percentage of silt. So you can see here where it meets. So here it meets, right? So this is that soil, whatever the sample you have brought in is clay loam. So for clay loam, it is classified as moderately high infiltration capacity potential. Okay, so that's how we do classification. And ABCD is this is the hydrologic classification of a soil depending upon its potential to generate runoff. All right. So again, if the value that you know for antecedent moisture condition for one curve is let's say the the antecedent moisture content was of antecedent moisture content category was type 2, but you want to compute for type 1, so that time you have to use this equation, okay. And again, if you know it, the value, the curve number for the antecedent moisture condition at ACM of 2 is known, and you want to convert for 3, then you can use this equation, okay. With this we can go ahead and solve one numerical. I'll simply run over this slide, okay. You please try to solve this problem yourself. Okay, so first thing is, in a catchment of 30 hectare 350 hectares, so area is given. The curve number value was assessed as 70, so this is curve number, it's already given for antecedent moisture condition 3, okay. So the information is, three information is given: area is given, the curve number value is given, and antecedent moisture condition is given. Estimate the value of runoff volume for the 4 days of rainfall. ACM on the first was of category 2. Now 3 is given, but it's saying for the first day the ACM was 2. So what do we do? First thing, we know it that 3 is given, okay, 3 is given, but we are asked to calculate for 2, so we have to use this equation to convert it for curve number, that curve numbers antecedent moisture 2, okay. The rest very simple. The storage is calculated by the formula which is given, 245 100 divided by Cn. Cn is 70 minus 1, okay. And then finally we calculate a runoff by this equation. Runoff, you simply put P minus 0.2 this equation, and then we generate runoff, okay. But here for the first case, please understand that for the 1st July, okay, for the 1st July, the antecedent moisture condition was category 2, but the value here, the curve number value is given for antecedent moisture condition 3, so you have to first convert that. Rest is straightforward. Calculate S, substitute the S in this equation Q, and that's what is required. That's it. Okay, this is SCNCN method. We have discussed now the rainfall runoff correlation. We have also discussed about the SCSCN method. Now there are some empirical methods. Empirical methods means, as I said, some experiment is conducted over one particular site, and based on the data that the person who has investigated derives an equation. And it is said that for Western Ghat in India, this equation can be used. For Deccan Plateau, this can be used. We should not be using it. Okay, and there's another Khosla's formula. Khosla's formula is very straightforward. He says that runoff is equal to rainfall minus losses. We know it, right? So that's what he did. So but this is calculates in monthly rainfall in centimeter. Okay, you have to provide this in centimeter. And the losses depends upon temperature. For temperature more than 4.5 degrees, this equation is used. Okay, and the rest is very simple. So for this question says you need to estimate the runoff. Temperature is provided, precipitation is provided, and you need to calculate runoff. And you know that runoff is P minus LM. So P, whatever the P value is, and LM is calculated based on this equation for temperature more than 4.5. So let's see for this one. So P is 4. So for 4.5, the temperature is 12, which is more than 4.5 degrees. So we use 0.48 times T, whatever the value comes, and we put it here. And then the precipitation minus losses will give us the rainfall. Okay. And I think it is also asking us to calculate the runoff coefficient. So runoff coefficient is summation of runoff divided by summation of precipitation. The ratio is what we call by the runoff coefficient. Okay, and finally the modeling. This is not included in your syllabus, but still I would like to touch upon this topic. Modeling here means, see, our study, our area, or our main real world is very complex. It has all the processes going on. Taking every nitty-gritty stuff from the real world would be difficult. So what we do is we do the survey of only the selected site. Okay, only the selected or a complete catchment of wherever we are interested. Only this much catchment, we cannot do for entire world. So that much catchment area is surveyed, and related informations like data and other informations are taken out. This information becomes input for our software. Software is in computer, and with the help of a computer we do simulation. The simulation here means the software itself is built using the equations that we have discussed. Yes, not the empirical ones, but there are other equations. One definitely is SCSCN method. So it uses that equation, it solves that equations, and finally it gives us an output. So modeling has input, processing, and output. There are three processes. Okay, and input itself consists of data collection and so many other stuff. Processing means now you bring the data, you clean the data, and you make readily available to be input into a software. You have to give the data in the format that software requires, and you feed the data to the software and click a run button, of course. Then the computer is going to simulate and will give you the result. Okay, so to summarize everything, the physical world we live in is very complex. We simplify it by ignoring the factors that are insignificant in the studies. Okay, and we take out only the required information. By simplifying the system, it enables us to predict its behavior with the help of established mathematics. Okay, so by simplifying the system means we are simplifying the real world system. See, we have now simplified, and then it's given as a input to the software, and with the help of established mathematics like conservation of mass, conservation of volume, and so many other stuff, SCSCN method, and there are so many other methods, right? We do the modeling, and modeling can be performed for various scenarios, like what happens if there's this much of rainfall occurs, what happens if the losses are less, what happens when catchment changes. So based on different varieties of situations, we can do the modeling, and we can predict what is going to happen. So with this, I would like to end this lecture. Thank you.